We present Refined DP, Diffusion Policy Fine-Tuning for Humanoid Loco-manipulation via Reinforcement Learning. Recent advances in motion imitation have demonstrated remarkable physical capabilities. However, many existing systems still rely heavily on teleoperation. As a result, they lack the ability to perform fully autonomous, whole-body tasks. This leads to a fundamental research question. How can we build truly autonomous humanoid robots? To address this challenge, we propose a hierarchical framework for humanoid autonomy. In addition, this paper focuses on fine-tune this framework to significantly improve task success rate and reliability in complex loco-manipulation tasks. The framework begins with a data collection pipeline. We first train a universal tracking policy capable of loco-manipulation with reinforcement learning. This controller can accurately track footstep commands and hand pose commands, enabling a wide range of tasks through teleoperation and scripted planners. The control policy adopts an upper body, lower body split. Each part is controlled by a separate policy. For the upper body controls, we could use randomly sampled hand commands to train an upper body policy. For the lower body, we train a stepping policy using reference motions solved from inverse kinematics. Building on this, we achieved stable walking, accurate stopping, and general hand movements. Here we use the MetaQuest as the control input. The handheld VR controller provides hand pose commands, and the joystick provides the velocity for the robot. Using this controller, we collect demonstration data for representative tasks, such as door opening and object transport. The dataset contains the robot observations, including object states, along with the corresponding action sequences. We then use this dataset to train a diffusion policy. After training, the diffusion policy serves as a high-level planner in our hierarchical framework. It generates task-level action chunks, while the low-level loco-manipulation controller executes these commands. This hierarchical design enables fully autonomous execution. To evaluate the success rate, we roll out the pre-trained diffusion policy in hundreds of environments in a simulator. For each environment, we initialize the robot and the object at different locations. As shown in the figure, the pre-trained diffusion policy on 50 trajectories achieve a baseline success rate between 50 to 70%. Based on this pre-training result, we continue to improve the pre-trained diffusion policy through reinforcement learning. We roll out the diffusion policy in a simulation environment and collect the resulting trajectories to further fine-tune the diffusion policy. The policy gradient method we adopted is from diffusion policy optimization. As shown on the right figure, fine-tuning increases the success rate consistently, improving from an initial 50 to 70% to over 90% across all tasks. Here, we compare the pre-trained diffusion policy versus the fine-tuned on a door opening task. From the side-by-side videos, the fine-tuned policy achieves a substantially higher success rate. Importantly, we observe that diffusion policies persistently reattempts when the initial attempt fails. This reattempt behavior is not present in the demonstration dataset, demonstrating autonomous, goal-directed behavior from diffusion policies. When we update the lower-level policy together with diffusion policy fine-tuning, the joint optimization achieves a lower tracking error and smoother motion comparable to fine-tuning diffusion policy alone, while achieving a comparable success rate. On hardware, we demonstrate Booster T1 performing autonomous loco-manipulation tasks. When execution fails, the fine-tuned policy automatically reattempts and successfully recovers, whereas the pre-trained policy often fails to do so. And if the environment changes on the fly, our method can replan and continue the task to completion. Another key observation is that fine-tuning significantly reduces the amount of pre-training data required, providing gains comparable to scaling the dataset by an order of magnitude. Since collecting demonstration data is expensive and difficult to scale, reinforcement learning fine-tuning offers a far more efficient and practical way to improve performance. In addition, we also find the fine-tuned policy achieves the same task faster. It eliminates some of the undecisive motions noticed in the pre-trained diffusion policy. Fine-tuning also helps the robot tolerate out-of-distribution scenarios. When initialized away from the box, fine-tuned policy is still able to complete the task while the pre-trained policy output ineffective actions and fail. Thank you for your time. We hope you enjoyed this presentation.